Hello and welcome to this lecture on advanced electric drives. In the last lecture, we are discussing about the modeling of a synchronous motor. We will start from that, and the modeling of a synchronous motor is more complex than the modeling of an induction motor, because in case of a synchronous motor, the rotor has also excitation. In fact, the rotor has got the field winding and the damper windings. So, let us see the modeling of synchronous motor. Now, here we can see here that we have a 3-phase machine, phase A, phase B and phase C. It is a synchronous machine and this is the stator. And the rotor has a salient pole structure. The salient pole structure means the rotor D axis is having lower air gap and the Q axis has a higher air gap. The air gap is not uniform and hence we call it a salient pole synchronous machine. So, this is our D axis along this axis, and the Q axis is orthogonal to D axis, as you already seen. This angle is 90 degree, and we have the field winding in the D axis and the damper winding in the D axis. So, in D axis rotor we have two windings, the field winding and the damper winding. Similarly, in the Q axis we just have one damper winding. So, we have seen in the last lecture that if we model a synchronous motor in rotor reference frame or in park reference frame, there is some distinct advantage that the inductances will be constant. We have a D axis inductance and we have the inductance in the Q axis, and they are constant, they are independent of the rotor position. So, we will be modeling the synchronous machine in rotor reference frame or the park reference frame, which means the reference frame is attached to the rotor and is rotating at the speed of the rotor. Omega is equal to omega r, and omega r is the speed of the rotor, and the angle of the reference frame is same as the rotor angle, theta equal to theta r. This is the angle of the reference frame, that is theta r, and this is same as the rotor angle. The rotor is rotating at a speed of omega r, and when it is attached to the rotor, when the reference frame is attached to the rotor, we know that it is rotating with the rotor, and hence the rotationally induced EMF will be appearing in the stator. The stator DQ windings will have the rotationally induced EMF which are present in this case. So, we can write down V ds equal to R s I ds plus P psi ds minus omega r psi q s. So, this is the rotationally induced EMF in the D axis, and similarly V q s is equal to R s I q s plus P psi q s plus omega r psi ds. This is the rotationally induced EMF in the Q axis, and the field winding is excited independently by a DC source. We have a DC source here for the field winding. This is the field winding and this is our field current. So, we can say here IF. So, VF equal to RF IF plus P psi F. This is for the field winding, and for the damper we have a D axis damper, and that is called KD. K stands for the damper. So, in the D axis we can write down VKD is equal to RKD into IKD, the resistance drop, plus P psi KD is the induced EMF, and the damper winding is usually shorted. So, we can make this equal to 0. They are meant for damping out the oscillation, and hence they are known as damper windings. Similarly, in the Q axis we have the damper winding, and that is also shorted. This is the Q axis damper winding, that is shorted. So, we can put that equal to 0, and that is equal to RKQ into IKQ, the resistance drop in the Q axis damper, plus P psi Q is the rate of change of flux linkage. And since the reference frame is attached with the rotor, there is no relative velocity between the reference frame and the rotor, and hence the reference frame windings, the rotor windings does not have any rotationally induced EMF, and hence we can see here that there is no rotational induced EMF in the field winding or in the damper winding in the D axis or the damper winding in the Q axis. So, we were discussing this in the last lecture, and then you know that when we want to transform the actual variables are the physical A, B, C of the stator. Now, when you take a rotor reference frame, we have to transform the variables from the physical ABC windings to the rotor reference frame rotating with the rotor, and hence we need a transformation matrix. And the transformation matrix is CS, we have already seen in the last lecture, and that is equal to cos theta r, cos theta r1, cos theta r2 minus sin theta r, minus sin theta r1, minus sin theta r2, half, half and half, and theta r1 is equal to theta r minus of 2 pi by 3, theta r2 is equal to theta r plus 2 pi by 3. And if we transform using this transformation, we can get the variables in the rotor reference frame, that is D, Q and the zero sequence component. But before we go for the rotor reference frame, let us try to understand how the machine is simulated in the ABC variables. Physically, we have phase A, phase B and phase C. We have 3 windings in this case. These are the stator windings, and this winding, this is AS, BS and CS, and each winding is having an applied voltage. So, for example, in phase A we can have VAS and this is IAS. Similarly, we can have the voltage applied to phase B, similarly to phase C. And we can have the currents in phase B and currents in phase C. So, we can write down the 3 voltage equation: VAS equal to RS IAS plus P psi IAS, VBS equal to RS IBS plus P psi IBS, and VCS equal to RS ICS plus P psi CS. And the rotor in this case has a field winding. We have a field winding, this is the rotor D axis, and we have a damper winding here, and in the Q axis we have a damper winding. So, this is KD, the D axis damper winding, and this is KQ, the Q axis damper winding, and this is the field, that is the field winding. The field winding is applied with the DC voltage, that is VF. So, this is the schematic view of a synchronous machine. We have 3 windings in the stator, AS, BS and CS. We have 3 windings in the rotor. We have 2 windings in the D axis, the field winding and the D axis damper, and we have 1 winding in the Q axis, that is KQ, that is the Q axis damper winding. So, we have to simulate this. So, we can write down the 6 equation. This is for the rotor. So, we have the equation for the stator and equation for the rotor, and these are the actual equation. And if we simulate this equation, these are differential equation, these are simultaneous 6 differential equation, and when we solve the differential equation, we can have the values of the various currents IAS, IBS, ICS, IF, IKD and IKQ, and when we have currents, we can find out the torque, and from the torque we can solve the electromechanical equation to find out the speed. Now, before we find out the currents, we have to know the various inductances, because these flux linkages are not directly available to us, they are available by the inductance. Okay. So, we can just write down what is the flux linkage psi ABCS. It means psi ABCS has got 3 components: psi AS, psi BS and psi CS. Psi AS, psi BS and psi CS are the three flux linkages in the three windings of the stator AS, BS and CS. And when we talk about one winding flux linkage, the flux is linked by its own current and flux is linked by the currents in the other windings also, because the whole machine is a electromagnetically coupled structure. So, if you want to find out the flux linkage in one winding, the other windings will also contribute to the flux linkage in that winding because of the mutual coupling. So, we can say here that this particular flux linkage can be written in this particular form, and we have AS, IAS, IBS, ICS, IF, IKD and IKQ, and I can have in this case LAA, the inductance of phase A with itself, the self inductance of phase A, we can call that to be LAA. This is LAB, the inductance of A with B, phase B of the stator, and we can say here LAC, the inductance of phase A with phase C of the stator, and then we have the rotor and the stator mutual inductances, that is AF, the inductance of phase A with the field winding, the inductance of phase A with the D axis damper winding. Write down the other rows also, LBA, LBB, LBC, LBF, LBKD, LBKQ, LCA, LCB, LCC, LCF, LCKD, LCKQ. Now, this inductance matrix is multiplied with the current vector to give us the flux linkage. So, we can divide this inductance matrix into two parts. This matrix is called LSS, the inductance matrix of the stator with respect to the stator, because LAA, LAB, LAC, they are basically the inductance of the stator winding with the stator windings. But LAF, LAKD and LAKQ, they represent the mutual inductance between the stator and the rotor. We call this part to be LSR. So, this inductance is LSS and this inductance is LSR. So, we can rewrite this equation as LAS, LBS, LCS is equal to LAA, LAB, LAC, LBA, LBB, LBC, LCA, LCB, LCC multiplied by IAS, IBS and ICS plus we have LAF, LAKD, LAKQ, LBF, LBKD, LBKQ, LCF, LCKD, LCKQ, and this we can multiply with the rotor currents, and the rotor currents are the field winding, the damper winding in the D axis and the damper winding in the Q axis. So, we have to evaluate these two inductances. Unless we evaluate these two inductances, we cannot do the simulation in the ABC variable. So, we have to know what is this LSS matrix and how does it vary with the rotor position, and what is this LSR matrix and how does this vary with the rotor position. Let us see. Now, this we will analyze in two parts. When we talk about LSS, we have the diagonal components like this and this. These diagonal components are the self inductance of the individual phases. The self inductance of A with A, the self inductance of B with B and the self inductance of C with C, and there are some off diagonal elements like this ones. Now, this represents the mutual inductance between the two phases, the mutual between phase A and B, the mutual inductance between phase A and C, and so on. So, we will first consider the self inductance terms like these terms, and then we will talk about the mutual inductance term which represent or which means the coupling between two stator phases of the synchronous motor. So, determination of stator self inductance of synchronous motor, synchronous machine. Determination of stator self inductances of synchronous machine. Now, we can find out the self inductance, and to be able to do that, let us first try to understand how the inductance is calculated. We have three different phases: phase A, phase B, and phase C, and the rotor is a salient pole structure. So, we have the salience in this case, this is the rotor pole, this is the rotor pole, and this is the D axis, and this axis is the Q axis. And these are the various stator phases AS, BS, and CS. Now, we can assume that the stator, each phase of the stator has a number of turns of effective number of turns of Ns. Ns is the effective number of turns of a stator phase. This also has got the same number of turns Ns. This also has the same number of turns Ns. Now, let us assume that this winding is carrying a current, that is IAS. Now, when we talk about the self inductance is the flux linkage in the winding due to its own current for its own unit current. So, we can first find out the flux linkage of phase A due to its own current, okay? And if we divide that by the current IAS, we get the self inductance of phase A. Now, this rotor is rotating at a speed of omega r. This may be rotating at a speed of omega r. It is not stationary, and the angle it obtains with the phase A is theta r. This is the phase A, and this angle theta r is the rotor angle. So, you know that when the rotor is rotating, phase A is alternatively seeing the D axis and Q axis, the D axis and the Q axis like this. So, the air gap seen by phase A is constantly changing. And if you want to find out the inductance, we have to define inductance in some special position. So, we know the inductance in the D axis, we know the inductance in the Q axis. So, these two inductances are known, or in other words, we know the permeance along two axes. Permeance along D axis is known, and the permeance along Q axis is known. So, we know the permeance along this axis, and we also know the permeance along the Q axis. So, if we want to find out the flux linkage, so we can start with the following. This LAA, the inductance of phase A with respect to itself, it consists of two parts, a leakage part LAL and magnetizing part or the mutual part is LAG. This is called the leakage inductance, and this is called the air gap inductance. Or the magnetizing inductance. And leakage is almost constant. The leakage is independent of the rotor position. So, we can assume that leakage remains constant. So, this part will remain constant, this part will be a function of the rotor position theta r. So, you would like to evaluate what is LAG. So, we can find out the flux linkage due to its own current. So, LAG is given as follows. It is IAS NS. So, this is actually the MMF produced by phase A, and this MMF is along the phase A axis, and we can resolve this MMF along the D axis. So, we can multiply here a factor cos theta r. Now, this MMF is along the D axis, and we know the permeance along D axis, that is P dg, and we can again multiply that with cos theta r, and again multiply with Ns. You know that when we multiply this with cos theta r, this is the MMF along the D axis multiplied by P dg is the flux along the D axis, and then the flux along this axis we can again resolve this back into the phase A, because we are trying to find out the flux linkage in phase A. So, when it is again brought back to phase A, we have again a factor cos theta r here, and then this is the flux, and if we talk about the flux linkage, multiply by the number of turns once again, and this is the contribution of the D axis. We know that we have two distinct axes, one is the D axis and the other is the Q axis, and the flux linkage is contributed both by the D axis and the Q axis. So, what we are trying to do here, the MMF is produced by phase A, we are resolving the MMF along D axis, multiplying by the permeance along the D axis, we are finding out the D axis component of the flux. We are again projecting that flux on phase A axis and finding out that component, and multiplying by the number of turns will give us the flux linkage due to the D axis flux. Similarly, the MMF produced by phase A can be resolved on the Q axis, and then we can again project it back on the phase A, that will be the contribution of the flux due to the Q axis multiplied by the number of turns of phase A will be given the flux linkage in phase A due to the Q axis component of the flux. So, this is the D axis component, and we can again say that that is multiplied by IAS NS into sin theta r into P QG. We are talking about the Q axis component. This is along this axis. We are again multiplying with sin theta r and Ns to find out the flux linkage in phase A. So, this is the total flux linkage in phase A, and its own current is IA. So, we can divide this by IAS. So, this is the inductance of the phase A with respect to itself, that is LAG. So, if we simplify this, what happens here is the following. We can take this Ns square common, and then we have cos square theta r into P dg plus sin square theta r into P qg, and this we can again simplify. We can convert this into cos 2 theta r, and then we can simplify like this. LAG equal to Ns square into P dg by 2 cos 2 theta r plus 1 plus qg by 2 1 minus cos 2 theta r, and that we can simplify again. Ns square P dg plus P qg by 2 plus P dg minus P qg by 2 in cos of 2 theta r, and that is equal to Ns square into Pg naught plus Pg2 into cos of 2 theta r. and that is equal to Lg naught plus Lg2 into cos of 2 theta r. So, Lag has got two components. One component is constant, that is Lg naught, and the other component varies with cos of 2 theta r, that is Lg2. So, if we plot this inductance variation against theta r, this is Lag, we will see that this Lag will have a constant term, that is Lg naught, and that will be a variable term which is Lg2 into cos 2 theta r. So, in fact, this will be changing in the following fashion. This is x axis, we have pi here, this is pi by 2, and this is 2 pi in radian, and then this will be Lg2, this amplitude is Lg2 because this is Lg2 into cos 2 theta r, and the base thing is Lg naught. This is the average value, that is Lg naught. And if we find out what is LAA, LAA is LAL plus Lg. LAL is a leakage inductance, so we can say here LAL plus Lg naught plus Lg2 into cos of 2 theta r. So, this LAA is the self inductance of phase A. Similarly, we can find out the self inductance of phase B, LBB, that is equal to LAL plus Lg naught plus Lg2 cos of 2 theta r minus 2 pi by 3, and that is equal to LAL plus Lg naught plus Lg2 cos of 2 theta r plus 2 pi by 3. And for the self inductance of phase C, similarly we can calculate LAL plus Lg naught plus Lg2 cos of 2 theta r minus of 2 pi by 3. So, we have been able to find out the self inductance of the three phases, phase A, phase B, and the phase C. Now, after finding out the self inductance of the stator, we can find out the mutual inductance between two phases of the stator, phase A with phase B with phase C, and phase C with phase A. So, we will now discuss calculation of mutual inductance between two phases of the stator. So, what we have here is that we have similarly phase A, phase B, and phase C, and the rotor is a salient pole rotor. This is the field winding or the field, the rotor field. This is the D axis. And this one is the Q axis. We have AS, BS, and CS. This angle that is obtained with phase A, this angle is theta r. Now, the definition of mutual inductance is this: it is the flux linkage of phase A current with phase B due to its own phase A current. So, we are talking about the flux linkage with phase B due to the current in phase A. So, this shows the mutual between the two phases. So, what we find out here is the following. See, if I say that is LAB, we can write down the expression each one is having a number of turns of ns, and ns. It is ns is into cos of theta r. This is carrying a current of is. Now, we have to find out how much of this flux produced by phase A is linking phase B. So, the flux is produced by phase A. We can resolve this component along the d axis, find out the flux here, resolve this component along the q axis and find out the flux here, and this flux is again resolved back onto phase B, and this flux is also resolved onto the phase B, and we can find out how much flux is linking phase B due to the unit current in phase A. So, that is what we can find out here. Ns into is into cos theta r in this case is the d axis flux due to the current in phase A multiplied by P dg into, we are talking about the projection of this along this axis. So, this angle is 120 minus theta, all right. So, so far as the cos is concerned, cos of minus theta and cos of plus theta are the same. So, we can just write down, in this case it is cos of theta r minus 120, okay, and then plus ns is, we can again find out the sine component for the q axis, sin theta r into p q z into sine of theta r minus 120, and that is multiplied by the number of turns of phase B. Phase B is having a number of turns of ns divided by the current of phase A, that is is. So, if we solve this expression, we will get the mutual inductance between phase A and phase B of the stator. Okay. So, if we simplify this, we can simplify this expression, and let me just give you the final value here, that is equal to n square into minus of half Pgd plus Pqg by 2 plus, I can write down in the next slide, Pdg minus Pqg by 2 into cos of 2 theta r minus of 120 or 2 pi by 3. So, if we further simplify this, we can write down the expression for LAB, the mutual between phase A and B, that is equal to minus of half Lg0 plus Lg2 into cos of 2 theta r minus of 2 pi by 3. 120 is same as 2 pi by 3. And out of symmetry, we can write down the inductance of phase B and C, that is equal to minus of half Lg0 plus Lg2, and what I can do is that I can replace this theta r by theta r minus 120 and simplify that. So, I will have here just cos 2 theta r. Similarly, for phase C, LCA, that is equal to minus of half Lg0 plus Lg2 into cos of 2 theta r plus 2 pi by 6. So, we see here that again in the mutual inductance also we have a function of theta r or 2 theta r. We see that LAB is a function of 2 theta r, LBC is also a function of 2 theta r, LCA is also a function of 2 theta r. So, when we simulate a synchronous machine in ABC variable, we have to update this inductance for every rotor position. So, that becomes a complex job, because all these things have to be done in iterative process, and this is going to take a lot of computer time. So, instead of simulating in ABC frame or ABC system, if we convert this into a DQ system housed on the rotor, taking the help of rotor reference frame, we can have inductance matrix which will be almost constant. So this is basically the self and the mutual inductance, and similarly we can derive the expression for the mutual inductance between the stator and the rotor. So right now we will be discussing about the mutual inductance between the stator and the rotor of a synchronous machine. So what we have here is this, that the rotor has got 3 windings. One is the field winding, and the other 2 windings are the damper winding. One is in the D axis and other is in the Q axis. So we have to find out the mutual inductance between the stator windings and the 3 rotor windings. So we have phase A, phase B and phase C of the stator, and this is the rotor, and this is the field winding, this one is the damper winding KD, and this is the damper winding in the Q axis, we can call this to be KQ, and the field winding is having an applied voltage of VF, and this is the stator winding, we can call this to be AS, this is BS and this is CS. Now what we will do here is this, that we will try to evaluate the mutual inductance between the stator winding AS and the field winding F. So this is the D axis, and this angle that is obtained with the axis of phase A is theta r. And the orthogonal axis is the Q axis. So when we find out the mutual between A and F, we can write down this expression LAF. Now what is LAF? LAF is given as LG0 plus LG2. Now this is the inductance in the D axis. We have already seen this, that if you see this expression in this case, that we have a maximum inductance and we have a minimum inductance. This is the inductance of phase A, the magnetizing inductance of phase A, when it is alternatively seeing the D axis and Q axis. When it is seeing the D axis, the inductance is maximum, so this is actually the maximum inductance, and this is corresponding to the D axis, and that is LG0 plus LG2, and this inductance is corresponding to the Q axis inductance, that is LG0 minus LG2. So the D axis inductance is LG0 plus LG2 and the Q axis inductance is LG0 minus LG2. So we have to remember that we have two definite inductances, one in the D axis and other in the Q axis. So this we can substitute in this, that in the D axis, if I say that this inductance is in this particular axis, so I want to find out the mutual between this and this. So this is my inductance, and the flux linkage will be into my IF is the flux produced by this, but this flux has to link this winding. So I have to multiply by a factor of NS by NF, and the component of this flux along phase A will be cos of theta r. So I have to multiply here cos of theta r, divided it by the unit current, that is IF. So this shows the mutual between the field and phase A. So, this we can simplify, that is equal to Lg0 plus Lg2 into Ns by Nf into cos of theta r. Now, similarly, we can find out the inductance between phase B and the field winding. Phase B is here. So, we have something quite similar to this. So, this will be Lg0 plus Lg2 into Ns by Nf into cos of theta r minus of 2 pi by 3, because B is shifted from A by 2 pi by 3. B is phase shifted from A by 2 pi by 3, and hence we have cos theta r minus of 2 pi by 3, the angle between the phase B and the d axis, 2 pi by 3 minus of theta r. And for the cos of minus theta is same as cos of plus theta, cos being an even function. So, I can write down cos of theta r minus 2 pi by 3. Similarly, we can have Cf, that is equal to Lg0 plus Lg2 Ns by Nf cos of theta r plus 2 pi by 3. So, this is the field winding. What about the damper winding? In a similar way, I can write down LAKD is equal to Lg0 plus Lg2 in Ns by Nkd into cos of theta r. And similarly, we can have LBKD, that is equal to Lg0 plus Lg2 into Ns by Nkd into cos of theta r minus of 2 pi by 3, and LCKD, that is equal to Lg0 plus Lg2 into Ns by Nkd cos of theta r plus 2 pi by 3. This is about the mutual inductance between the stator winding and the d axis damper. And similarly, we can evaluate the mutual inductance between the stator winding and the q axis damper, and that is LAKQ. So, we will see what is this inductance. We are finding out the inductance between A and KQ. This is my phase A and this is KQ, and what multiply by a factor of cos theta r plus pi by 2, and cos theta r plus pi by 2 is minus of sin theta r. So, the expression will be multiplied by minus of sin theta r for phase A, and similarly for phase B and C we can change theta r appropriately to theta r minus 2 pi by 3 and theta r plus 2 pi by 3 respectively. So, we can see what is this inductance, the mutual inductance, that is Lg0 plus Lg2 into Ns by Nkq into sin of theta r with a negative sign. LBKQ is equal to minus Lg0 plus Lg2 Ns by Nkq. Okay. Here actually that is a very interesting thing to note, that the inductance in the q axis is not Lg0 plus Lg2. It is in fact, if we see little before, what we have seen in this case is that the inductance in the q axis is in fact, this is the inductance, and this inductance is Lg0 minus Lg2, and we will see that this Lg0 plus Lg2 is equal to, there is a inductance called the d axis magnetizing inductance. We can call that to be LMD, and little later we will show you that this LMD is equal to Lg0 plus Lg2, and this is a factor of 2 by 3. And similarly, Lg0 minus Lg2 is the q axis magnetizing inductance, and that is equal to 2 by 3 times LMQ. LMQ is the magnetizing inductance in the q axis. So, when we are talking about the q axis inductance, we have to take Lg0 minus Lg2. So, in this case what we have here is, we have in this case Lg0 minus Lg2 and Lg0 minus Lg2 sine of theta r minus of 2 pi by 3 and L say CKQ is equal to minus Lg0 minus Lg2 ns by nkq sine into theta r plus 2 pi by 3. And we have already seen that Lmd can be given as 3 by 2 Lg0 plus Lg2. This is the d axis magnetizing inductance referred from the primary side, and similarly Lmq is 3 by 2 times of Lg0 minus Lg2. Now, this Lmd and Lmq can be obtained by suitable transformation. So, these are the mutual inductance, and it looks little complicated because this is a function of theta r. Now, when we transform this inductance into the rotor reference frame, the 2 axis rotor reference frame, we will see that these inductances will be independent of theta r. Okay. So, we will see that now we can say in the following fashion that we have these inductances and we can transform the equation all right. So, what we have here is the following. We have psi ABCS, that is equal to LSS is a matrix into IABCS plus LSR into IF KD KQ, or we can write down in the following fashion: psi S is equal to LSS into IS plus LSR into IR. IR is the rotor, and the rotor has got 3 components of current: the field winding, the D axis damper and the Q axis damper. And the stator has got 3 components: phase A current, phase B current and phase C current. The psi S is also having 3 components. So, we have already seen this earlier. We can see this, that this is the component that is LSS and this is the component that is LSR, the mutual between the stator and the rotor. Now, we would like to transform this into the DQ equation. So, if you want to transfer this into the DQ equation, we will pre-multiply this with the transformation matrix, that is CS. C is the transformation matrix, and this also we have seen, this matrix is the transformation matrix, which is in the rotor reference frame, and this is a function of cos theta r1, cos theta r2 minus sin theta r, minus sin theta r1 and minus sin theta r2, half, half and half, 2 by 3, and this 2 by 3 is coming to picture to have per phase power invariance. It's a transformation where the per phase power is maintained in the 3-phase system, same as that of the 2-phase system. So, when we use the transformation, we can transform these fluxes into the DQ fluxes. So, we have CS, LSS. This LSS we have already evaluated. LSS has got the self inductances and the mutual inductance between the stator, 2 phases of the stator. So, this we have evaluated. This also we have. So, this is CS inverse and CS into IS vector plus CS LSR into IR. Now, what is CS into psi S? This ABC will transform into the DQ. So, we can say here this is DQOS. and then this matrix after transformation will have the following values, and then when we transform this CS into IS, that will be IDS, IQS and IOS, and this matrix CS, LSS and CS inverse, if you calculate this particular matrix, this matrix will have the following form. So, we have LMD here 0 and 0, LMD plus LAL, in this case we have 0, LMQ plus LAL 0 and 0, 0 and LAL. So, we see that the d axis inductance, so we can call this LDS if the d axis inductance is LAL plus LMD. And what is LMD? LMD is evaluated as 3/2 times LGO plus LG2, okay, and LQS is equal to LAL plus LMQ, and that is equal to LAL plus 3/2 times of LG0 minus LG2. So, we see that the inductance matrix in this case, we can call this inductance matrix to be LDQO matrix, and this LDQO matrix is fortunately is a constant matrix, unlike the matrix LSS, which is a function of theta r. After pre multiplying with CS and post multiplying with CS inverse, there is lot of simplification involved, and this matrix that we are obtaining here is LDQOS. That matrix is having constant inductances like LMD, but interesting because when we are transforming into the rotor reference frame, we are seeing that the inductances here are constant inductances. Plus, this matrix also, if you simplify, this is also will be appearing in the following fashion. The currents will also be transformed. So, we have the transformed currents here, IF prime, IKD prime and IKQ prime here, and this matrix would be LMD, LMD and 0, and then 0, 0 LMQ, and then we have 0, 0 and 0. So, we have the inductance matrix referred in the rotor reference frame. So, we can write down the various flux linkages. The flux linkages in the d axis is given as LDS into IDS plus LMD into IF, the referred current, plus IKD, and the flux linkage in the q axis psi qs is equal to LQS into IQS plus LMQ into IKQ. The flux linkage in the field referred from the primary side is equal to LF into IF plus LMD into IDS plus IKD prime. The flux linkage in the d axis damper is equal to LKD prime IKD prime plus LMD IDS plus IF prime, and the flux linkage in the q axis damper referred from the primary side is LKQ IKQ plus LMQ into IQS. So, these are the 5 flux linkages in the 5 windings, because we now have 5 windings, 2 winding in the stator, we have D and Q winding in the stator, and 3 windings in the rotor, 2 windings in the D axis, the field winding and the damper windings in the D axis, and 1 winding in the Q axis, that is the Q axis damper, and these are the 5 flux linkage equation. referred from the primary side. When we draw the equivalent circuit, we have to understand that all the variables are referred from the primary side, and hence we have to multiply by appropriate number of turns to get the variables in the primary side, and these variables which are referred from the primary side are designated. The rotor variables referred from to the primary side are shown as the prime variable like psi f prime, psi kd prime and psi kq prime. So, we are now gradually developing the model of an induction machine in the Park reference frame in dq equations. In the next lecture, we will see that how this model is utilized to derive the expression for the torque, and from the torque how we can find out the speed, and how we can simulate a synchronous machine in dq equivalent circuit to get the response of the machine.